Okay, and I want to turn it back to sharpless epoxidation, this asymmetric epoxidation reaction, because he actually developed this reaction in which you start with a reagent called the aryl alcohol. This is a allylic group, allylic carbon. You have your carbon-carbon double bond from alkene. So the first is vinyl, then aryl alcohol, right, into epoxy alcohol, epoxide, triangle, CCO, okay, COC bond. It's a cyclic ether, right? So using this reagent called the tert-butyl hydroperoxide. So when you see a OOH, right, this is a very good oxidizing agent, right? With your catalyst, your titanium tetra isopropoxide, TiO, this I is isopropoxide tetra, so 4 of them here. And either the plus or the minus diethyl tartrate. Tartrate is a chiral ligand here, okay? So but the thing is, right, this reaction is only effective for its aryl alcohol, which means if you have one more, or you have vinyl, then just too bad, you don't have a functional reaction here. Now, because the reason is because of this enantioselectivity, right? This activation group here, that's by the pre-coordination of the alcohol functional group, this oxygen with lone pair, onto the titanium center. Because we have a D block titanium, you can have the partially vacant d orbital take a whole this ligand donation from the oxygen. So that's why you cannot use other unfunctionalized alkene like your alkyl, aryl-substituted alkene. They do not work because they don't have this 2 bond away from this pi electron club with oxygen of lone pair. Okay, so I hope you understand. Now, the other bit is, let me continue. So this is scheme 2 here, right? So we talk about the next work by Jacobson. So of course he didn't win a Nobel Prize here, but we need to recognize him. This is why we do this experiment. And Jacobson and co-worker then discovered this using a manganese-based complex, right? They have a very good stereoselective non-bonding interaction with the unfunctionalized alkene. So you see, this is how scientists progress. You research, publishing findings, we still have problems and challenges. So just now for sharpless, you must have an aryl alcohol. But what if we don't? We don't need it. Do we want to do multiple steps to have the aryl alcohol and take it away? No, right? We waste yield and time and resources. So we say, there must be a way. We try, never give up. So Jacobson and his co-worker started with this tetra-substituted alkene, unfunctionalized alkene, and do oxidation, and he was able to convert it into this epoxide. Now, so you see, right, because epoxide, if you have the R1, 2, 3, 4, that's all different here. When you have the suprafacial and parafacial attack to form the oxygen triangle ring, these two are not the same. We want to turn the molecule and see why they are not the same. Okay, it's chiral. And the catalyst he used was a manganese-based catalyst, right? And has shown as good effect there. So we are hoping that you can do something in the lab, maybe virtual lab. Yeah. So this is the scheme. In the current experiment, you will prepare the Jacobson's catalyst here, where you have a possibility for it to convert into the Jacobson catalyst. Why do we say there's a possibility? It's not a certainty, because it depends your skills, depends whether it can survive the conditions, right? But you follow the synthesis, you can get there. But if you don't have such a very good inner environment, maybe it will be destroyed. It's about, after all, your experience, right? So let's now go to experimental. Now the first thing to do is you need to know what chemicals that you'll be using in the lab here, right? So safety precautions number 1. You can do anything right, but safety is not right, then too bad you have failed. Methanol, ethanol, acetic acid, flammable, right? Don't drink it, no matter how thirsty you are. This is a vinegar, right? Smells good, sour, right? And your 1,2-diaminocyclohexane, very corrosive, okay? So it will cause your skin irritations. Just don't touch it. Wear your nitrile glove. And the chloroform D, when you prepare your NMR and your dichloromethane, these are carcinogenic, right? But using a small amount, so it's fine. So your chloroform CdCl3, your CH2Cl2, methanol, tartaric acid, your 3,5-di-tert-butyl aldehyde, potassium carbonate, and Jacobsen ligands are toxic. Toxic means don't get in contact with your hand, with your skin, with, you don't swallow it, okay? Wear your PPE, lab goggles, gloves, and your lab coat, cover shoes all the time. Also, your chloroform D, dichloromethane, acetic acid, potassium carbonate, tartrate acid, 1,2-diaminocyclohexane, and your 3,5-tert-butyl and the Jacobsen Ligand are irritant, okay? They will cause you to scratch, maybe a bit of red, rashes. So again, avoid skin contact and avoid inhalation. So that means you have to perform all this transfer of chemicals, withdrawal chemicals in the fume hood, please. All right, and also must be well ventilated. So do refer to the safety data sheet of these chemicals for your safety information and do the risk assessment. Okay, if you're asked to. Now, part 1, right, of this synthesis scheme, you have a resolution of amine, because we give you a racemic mixture of this diamine. So you need to first separate the two forms, and the way to do is you add to 100 ml round bottom flask this L plus tartaric acid, right? To dissolve with a DI water first, right? We stir it, do it at room temperature. Now think about why room temperature, not heat it up. Normally you want to heat things up to speed up the reaction, but not in this case. Just think a bit more. And then you add this 6.1 ml of this 1,2-diaminocyclohexane, and it's a mixture because of how we show the bond here, right? Dropwise. Why dropwise? Dropwise because you want it to form the crystals. You form it ionic. Now, you have an amine group, you have acid group here, but it's a weak acid and weak base, so you want it to have time to transfer the proton in the acid-base reaction and to form this ionic bond. That is not weak, but not as strong as your potassium chloride or sodium chloride. So you need to do it dropwise. It may turn cloudy. Why is that so? Why turn cloudy? Look at your solvent. Look at your compound. Why does it turn cloudy? Cloudy means you have a precipitate, which means it's not soluble, okay? But after a while, it can dissolve. So do ask yourself, why are these observations, taken? Now, of course, because the trans and cis ratio of this diamine, right, you can take it as a 1:1 just for calculation's sake. If not, what you can do is you can check for the polarimetry test before the reaction. Now, if you don't see that you have a full dissolution, right, it's not transparent, you still see cloudiness, then you can just heat it a little bit up because you want to dissolve. So why raising temperature will help to dissolve your precipitate, because it's about your solubility product constant, right? You raise temperature, you have you can shift the equilibrium to the one side, okay? Or you can add a bit more solvent to dissolve it. Now always use a condenser when you heat up the solution, because these chemicals are quite volatile. You might lose it if you don't put a condenser, okay? The next part, okay, is after you have dissolved everything, add 2.5 ml of this glacial acetic acid. What does the word glacial mean? Means 100%, 99.9%, right? Is it super pure into one portion? Now then you see there will be a precipitation. Okay, what color? You tell me in your report here. You can see that the glacial acid, right, is corrosive because of its super high concentration. Like glaze, like glaze means glass. Glass is not sorry, ice cream. Okay. Or the glass. Do not consume this do not disturb this small size crystal, right? Because you want it to have a large surface area, right? To trap the impurities. Because when it's forming your crystals, right, you also collect some of the maybe some dust or things you do not want there. And then after that, you try to cool in the ice bath for half an hour, and then you perform subsequent filtration. You rinse it with cold water, 5.0 ml, or just not too much because it can dissolve. It's cold because if it's warm, you can dissolve a crystal. You do some U, and then followed by your rinse it with 4 times of this methanol here. Methanol is to remove these impurities that's organic. Okay. So the next part is you purify by the recrystallization using minimum amount of boiling water to maximize the yield here. If you don't see it's a clear solution, you have some insoluble solid form, do a hot gravity filtration, right? So do that. and then allow the solution to cool, collect the crystals from the top, right? Do suction filtration, scrap it. Don't scrub too hard because you might take out the lint from the filter paper. If you do not see any crystallization occur, add a bit of this your methanol dropwise to reduce the solubility. So then you see a sudden gush of these crystals, right, by adding more to the filtrate. So for more information, for revision, please scan this QR code and watch this recrystallization video. Okay. Now let's continue here. So this is what you expected to see here. All right, your crude product collected from the suction filtration, your RR12-diaminocyclohexane, mono plus tartrate. And then when you do a recryst, right, you see a bit of product here. It's shimmery, shiny, because it's a pure crystal. And then you recrystallize to purify it, right, it's even more here, okay? Very happy looking crystals. Yeah. And then for part 2, to make your Jacobsen's ligand, so to a 100 ml round bottom flask, add this RR12-diaminocyclohexane, right, this salt here, and then you potassium carbonate, right, 2 equivalents, and you calculate this to be the amount, water. Here you can see which is the limiting reagent, right, you can calculate and see. Then you mix it and stir until the dissolution is achieved, right, and then you add 22 ml of the ethanol, or pardon this, you add it and reflux, you start the reflux. Okay. If the product is less, the amount of the other reactants can be scaled down accordingly, because remember we assume to be 100% yield, and then you have 2.1 millimole and the rest will follow. Okay, but if you have less from a previous step, you need to adjust it, you can scale down. Next, to this beaker, you add this aldehyde, dissolved in a 10 ml ethanol with careful heating. Then you add it to a round bottle flask with a glass dropper. You need to add it to dropwise, this aldehyde here. Okay, and you can add it from the top of the condenser, the top here, right? The top, although it's a long opening, but you can just drop it. You don't have to remove the condenser because people make mistakes and they crack and spoil the reaction mixture. You're going to keep the condenser, add from the top. Then you rinse with the hot ethanol, reflux for an hour. With flux means you have your continuous evaporation, condensation in the column. And after a while, because it becomes very sticky, right? So it becomes like a fudge, very hard to stir. You might need to add some solvent to dissolve it to make it dilute, and you can move. If not, you just see the stirring bar, no shaking, nothing stirring. It's not going to be complete. And if stirring is very difficult, you can use the mechanical action from your hand, glass rod, break the large part of the solid here. Then you ask why? Why is it like a sticky solid? Why is it so hard? What's inside there? What's inside there, right? You have some manganese, right? You have a big molecule, lots of intermolecular forces of attraction. Is it even ionic? Next part, water, you add it, make sure it's cool in ice bath for half an hour. Then you see something yellow. Okay, collect it using suction filtration. Wash with 5 ml of the ethanol. And of course, you can have more ethanol wash if your yield is higher than usual. Then you dissolve this you dissolve this solid into dichloromethane. Extraction, right? Extraction. Organic layers, sodium sulfate, Na2SO4, okay? Spot the mistake, Na2SO4. And drying agent is then removed by filtration. So the pumping can be very easy, right? Easily observed because you see, you can see that they have different solvent inside, and because CH2Cl2 is super volatile, low boiling point, so you can see that some parts become vapor, and you see some bubbles evolving from the flask. So you might be more careful there, okay? But don't be alarmed. Then the solvent is being removed by rotovap to form a yellow solid. You have done that before, and to revise on your technique, which you need to answer some questions, please check out this video here, QR code. Now voila, this is how it looks like, your Jacobsen's catalyst, crude yield collected by suction filtration. Do we purify it? Okay, we wait. So first, you want to characterize it. So we have two purposes here. One is the product NMR. You prepare by taking out, you weigh 10 milligrams of it, dissolve it into the tube, NMR tube, 0.6 ml. CCl3. Don't add the chlorophyll, is the deuterated chlorophyll, because if not, it's not visible. This is the expected NMR spectra after you do a MNOVA, right? This is from a student. You can see how it looks like. And then this is an NMR spectra obtained from literature. Do a little comparison here. Okay, how you analyze NMR, please do a recap. Okay, last part is your polarimetry analysis. This is to check the rotation, angle of rotation, the angle. So you prepare this, how to determine its optical purity. What is the enantiomer excess? You weigh accurately 0.5 to 1 gram of your Jacobsen ligand and then dissolve it into your dichloromethane, your 10 ml volumetric flask. So now you have the exact concentration. Okay. Then you determine the optical rotation using the cell. Okay, 1 dm. 1 dm is your 10 cm, your cell here. No air bubbles. Right? Why no air bubbles? Your pathway is 10 cm, your 1 dm, right? If it's bubble, then it's no longer a solution path. You don't have the same concentration, and you know that when you pass a ray of light through a bubble, do you experience a bending of light due to a different refractive index of air in your solution, right? So ensure there's no bubble, very critical step. And you minimize the evaporation of the dichloromethane solvent. After you measure this, discard the DCM, not so healthy, and then discard from the cell and also the volumetric flask, right, in a chlorinated waste solvent. Get the boy. Then you can also recover the ligand, okay, because this is not very affordable. It can become expensive. You can weigh the specific rotation, press on the button, and then see the alpha value. How to do it? Again, I've put down the QR code for you, have an easy reference. So with that, I end off today's lecture, a short lecture on the theory background and the synthesis of the Jacobsen ligand synthesis, and hope you enjoy the process. These are the credit for the slides and the resource from the Senpai Learn team. So to check out more, do contact me. Yeah, and I will see you in lab. Thank you and take care. Cheers.